citizens and government policymakers be making fear model misspecification. So they are going to experience both risk and uncertainty. So what risk is a kind of ignorance described by a unique, well-understood probability distribution. That's how people are evaluating things in the rational expectations model. Our people are not going to have a unique probability distribution. So there's both going to be risk and uncertainty. So, why did Lars and I get interested in this? So here's a way to just summarize finance, findings in finance, which are beautiful and empirically. There's a huge set of, you could call them empirical failures or empirical puzzles. And it is that prices of risk that are measured in the market, so this would be the equity premium puzzle or lots of other so-called puzzles, prices of risk seem way too high to be rationalized by any expected utility model. You need measures of risk aversion that are astronomically high to explain the risk premium that are observed. That's the equity premium puzzle. And Lars has a list of 52 other puzzles that come down to the same thing. So when Lars writes a paper, Consumption Strikes Back, it's all about that. So I'll come back to that. So we're going to make the hunch is that those things that are that are interpreted as risk premia under a communist model, rational expectations model, aren't really risk premia. They're compensations for bearing something else. That's the idea. That's the hunch that attracted Lars and me to this. Oh, I'll put my cards on the table. There's something else that attracted Lars and me to this. I was wandering around the Stanford bookstore and I found a book. That's the reason. So here's the history of here's a digression on personal history. So like in graduate school, really badly trained. So I was trained in a graduate school where math was discouraged because the faculty didn't know any math. So it made fun of math. So you could just reason anything. Okay, so anyway, come out of graduate school and go to the real world. You run into some guys who know some math. Okay, so then, kind of interested in dynamics. So then what you have to do is you have to learn some dynamic programming, which you have no idea of. So this is Sargent in the early 70s. Have no idea. So what you do, you have to learn what a contraction mapping is, a metric space. So if you finally work your butt off for like 5 years and you learn some dynamic programming and you learn some linear prediction theory, then you can write some papers. Okay. Now, if you do dynamic programming, the assumption behind dynamic programming or linear prediction theory in the math literature is the model is correct. Backward induction, you're using the model is correct, a unique model. Often you're using Bayes' law with a correct model. You do that, okay. So we did that, get 20 years of writing papers with Bellman equations and so on. So then in the early 90s, I wandered in the bookstore, and dynamic programming was good to me then. Let's see pick up a book on optimal control. And now, the Bellman equations have changed. And why? The books are about robust control. So what's that about? The engineers and mathematicians discovered that when they used dynamic programming to control physical systems, like shooting rockets to the moon, the dynamic programming didn't work. So why didn't it work? I mean, they sent, the rocket was supposed to go to the moon, and it was supposed to be stabilized at a trajectory. Instead, it went to the sun. And so the question is, what failed? So one thing is, you blame your research assistant and the Python program and the MATLAB program. No, that wasn't right. Blame the dynamic programming. You skipped, I don't know, no, that worked. You were solving the Bellman equations correctly. What's left? Your objective function was wrong. No, you wanted to go to the moon. What was wrong? Your model. With all due respect, your engineering and physics was wrong. So now what do? So thing A is, well, don't send anything more to the moon until you improve the physics. So they said, forget that. What we're going to do is assume the model is wrong. And we're going to surround our model by a set of other models. And now we're not going to be able to describe it just in a vague way. It's just going to be, it's an error term, or it's going to be a likelihood ratio. And that's what's really governing the data. And we're going to do a min-max expected control theory. They did that. That's where Lars and I, that's what's in this book at the Stanford bookstore. So it turns out they modify the Bellman equations. And here's the deal. Every step, and it's easy to do. I'll show you how to do it if you're a graduate student. Because you're writing Bellman equations. Every place you have max, you put min-max. And you go back one step. And it turns out the min step, you can exchange orders of min and max. Why? So if Debraj were here to say, what entitles you to do that? I'd say, because it's a zero-sum game. So these games have lots of beautiful structure, and you can exchange orders in which players play. Anyway, so you do that. So Chris Sims told me this shouldn't impress me. This impressed me that if physicists and engineers don't trust their models, and they make decisions using this kind of control theory, I shouldn't feel so bad that I don't trust my model. That's the idea. So we're going to make our agents like that. Okay. So so now here we go. So how does it affect equilibrium concepts? So here's the deal. Okay. So notice, once you say you don't trust your model, and remember I told you the rational expectations equilibrium concept, that's a fixed point in a mapping from a perceived law of motion, or from a perceived model to an actual model. That's the communism. Once I say people don't trust their models, all hell breaks loose. It subverts the equilibrium concept. You don't even know how to start. Because we're going to put heterogeneity of models on the table. So here's what Lars and I do. We make some choices, and we have a philosophy. We stick as close as possible to the rational expectations philosophy. And you see what I mean. So our equilibrium concept, we're going to assume that we have the notion of an approximating model. It's a model that everybody agrees on, but distrusts. See with me? That's going to play the role of this communism. So the communism is going to be weakened. Everybody's going to have that same model, but they're going to distrust it. So they're all going to surround it with a ball. So with that, we can actually extend a Nash or subgame perfect equilibrium, what's called a self-confirming equilibrium, or a recursive competitive equilibrium. So that's what we do. I might say a little more about that.
Can I ask a question?
Absolutely.
You had your model was shared with nature,
Ah.
and now you have doubt about the model. So that's the one part I didn't understand.
Yeah. You noticed I didn't say anything about nature. Okay, so here's the deal. Here's the deal. So it's logically, okay. So I'm going to draw the following distinction. When I build a rational expectations model, when I construct that fixed point, that's all pure theory. That's all pure theory. And I don't have to say anything about nature at that point. But then the key point is when I do empirical work and I match to the data, that's the point at which I say, well, what's actually generating the data? It's at that point that I add the nature thing. Like an Error-Debreu model that has lots of randomness stuff, it says nothing about nature. It's just pure theory. Okay, but when I do the empirical work, I have to add. So what Lars and I are going to do, this is heroic. We're going to assume, you might not like this. What Lars and I are going to assume is this fear of model misspecification in the end of the day is just in people's heads, and nature is actually generating the model using the common approximating model. And I'll tell you where that's used. That's used at this last step to construct the likelihood function. Because I'm going to have to say when I write down a likelihood function or do any kind of econometrics, I'm going to have to put my money on a particular model that's generating the data.
So do all agents have the same set of beliefs?
They don't have to be, but let's say they do. Let's say they have the same set of models. I can have agents with different sizes of balls. I can accommodate that. But the most fun thing is to say they have the same set. But then you can see what's going to happen. They're all going to be min-max guys, but they have different purposes. So after I exchange orders of min and max, it's going to look as if you and I have different. At the end of the day, it's going to look like you're a Bayesian because you're maximizing with respect to a particular model in this set, and I'm going to look like a Bayesian too, ex post. But it's going to look like we have belief heterogeneity, and it's going to be a reflection of our doubts of the model. So this is a way of in a disciplined way, inducing some ex post. Where ex post means, after our behavior. That's the idea. But this question is a critical one that concerns Lars and me. And that decision is not the only thing you can do. I'll say, this is a digression, but you can say the following. Okay. See, once you get cast out of, you get cast into the wilderness away from rational expectations. It's nasty out there, and you spotted something. So one thing you could say is, wait a minute, scratch your head. How do you learn if you don't have a unique model? Because the dominant theory of learning is Bayes' law, and the way several of my friends put it is. A Bayesian knows the truth from the beginning. And you know what that means is it has a probability distribution over a sequence. That's his model. And he has some data. And all he does is he updates. Never revises his view about what that original probability distribution was. He's just using Bayes' law. But what happens if you have multiple models? How do you learn? So there's some takes on that. Anyway. So the applications that I described, where Lars and I assume that Lars would say this fear of model misspecification is just all in people's heads. That's a particular way of doing the empirical work. There are other ways you could do it, but that's an open area. Okay, good. So just what I said. That's what we assume. You can get a disciplined model of belief heterogeneity. The reason Lars, so some people are picking this up, actually. Anmol Bhandari, a recent graduate of here, I think, picks up some of this in his PhD thesis, in his paper. The reason that's of interest is there's a literature in finance following from Harrison Krebs that also some literature in general equilibrium theory that has exogenous belief heterogeneity. And what's troublesome about that is, so Lucas said, beware of theorists bearing free parameters. The beautiful thing about rational expectations is that it eliminates any free parameters having to do indexing people's beliefs about endogenous variables, because they're outcomes. They're the result of that fixed point. But when you build a model, if you look at Harrison Krepp's beautiful paper in 78QJE, which is a model of bubbles with optimists and pessimists, what drives the model is you exogenously make up who's an optimist and a pessimist. You make that up. That adds lots of parameters. So this may be a way to discipline this by adding very few parameters. Actually one. Okay. So now I'm going to just go down. What does it do to quantities? So what does fear of model misspecification do to quantities? So here's something that happens, at least the way Lars and I do it. An increase in model uncertainty operates like an increase in the discount factor with respect to quantity. So, like, what's the big deal? So what it does is things like this. I'll give you a concrete example of this, which is beautiful, with a permanent income model. So it makes you more patient. So it will do things like induce a kind of precautionary saving. So you could say, if that's all you get out of it, why not just increase the discount factor in a model? So I'll come back to that. So there's actually an observational equivalence between a discount factor and a single parameter Lars and I call theta, which indexes the size of this ball. So let me talk you through the precautionary saving, because this kind of shows you what's going on. So do you know the simplest version of the Friedman permanent income model under rational expectations? So here's the model. Person wants to maximize expected value of summation beta to the t u of c of t. U looks like this. Okay. The person can invest in a risk. There's only one asset. Can't insure. The person has to self-insure by saving. The gross interest rate, it's risk-free, it's called R. Beta times R is equal to 1. That's what effectively Friedman assumed. Now we have an income process that looks like this. There's a stochastic process for income, which is income is Y. It's governed by some stochastic process. So Friedman or Hall or Brock and Meerman assume that the agent knows that process. That's the one source of randomness. That process is moving along. So what does Friedman's agents do? Friedman agents completely smooths. It's insofar as possible, it tries to smooth consumption. Makes consumption actually look like a random walk and makes its assets look like a random walk. So a shock comes in. Okay. That's under rational expectations where you know the distribution. Okay. So what the person's doing is smoothing his consumption and using a shock comes in and the agent tries to figure out is that shock permanent or transitory, divides it. The permanent shock he eats, increases consumption a lot. If it's transitory, he saves most of it. That's it. Now we just do the same model, but now the agent does not trust the probability distribution for this stochastic process. And there's this there's a ball of models that are close. Okay, so if you're a time series econometrician, you know what features of a model are hard to estimate and which are easy to estimate. Just a digression. The ones that are easy to estimate are high frequency things. Things that are high frequency, if you do a frequency decomposition, those are easy to learn about because the law of large numbers cuts in really fast. But really low frequency things that are very persistent, those are very hard to learn about. Just because dependence arrests the rate of convergence associated with the law of large numbers. The evil agent who's using entropy knows that. So here's what the evil agent does. So you do this max-min, the evil agent, the minimizing agent says, okay, I know what you're doing. You're doing this permanent income, Friedman permanent income thing. So at the high frequency stuff, you're doing fine. You can self-insure that. So what I'm going to do is I'm going to put all the misspecification at the really low frequency end, because you can't, that very persistent stuff, you can't self-insure about that. So try to fix that. So then what the maximizing agent does is says, okay, I know that's where I'm most vulnerable. I'm going to increase my savings. I'm going to do precautionary savings. So there's a different kind of precautionary savings than the standard one in the literature that just depends on the convexity of the margin. I'm being off a derivative of margin utility. So that's where the beta thing comes in. That's what he does. So it's like I'm making you more patient so you save more. So that's what happens here. So that's kind of boring, though, just on quantities, because now there's an observational equivalence result. There's a beta, theta, you can't tell the difference. So can I make a confession how Lars Hansen and I discovered that observational equivalence? We discovered on the computer. We didn't know that. So we did maximum likelihood of beta and theta, and the likelihood function comes back. It's a ridge. It's just a ridge. And then we did some theoretical work and discovered there should be a ridge. Okay. Now what does it do to prices? What does it do to prices? So the answer to that is if you just look quantities alone, like Prescott does in real business cycle theory, and Lucas does, they ignore asset prices. You won't get anything from this. This will give you no kick in real business cycle theory unless you look at prices. Okay, but what does it do to prices? What it does is it does a lot. What it does is, if you speak stochastic discount factor language, it takes the standard stochastic discount factor and it multiplies it by actually a likelihood ratio that's potentially volatile. So it makes it look as if there's a random shock to utility. And the logic of this is simple. Under the approximating model, expected utility would be a certain thing, but the person who is not evaluating things under the approximating model, he's doing min-max. So the minimization puts a likelihood ratio into the expected utility. And that likelihood ratio, a likelihood ratio is just a random variable or a stochastic process, and it bounces around. So the whole equity premium, puzzle is that beta times u prime of ct plus 1 times u prime of ct. If you put in aggregate or individual consumption data, that doesn't move around enough. But now under this theory, it's beta u prime of ct plus 1 u prime of ct times this likelihood ratio, and that's moving around. And that thing moving around, that's not representing risk, that's representing uncertainty. So the punchline is portfolio holders' worst case beliefs affect state contingent prices, and this gives rise to a market price of model uncertainty. So this helps to attain these so-called Hansen-Jaganathan bounds by increasing the volatility of the stochastic discount factor. Again, your question, under the common approximating model. So I think of this as a refinement of rational expectations. Even if you hate this, it actually teaches you, it reminds you of all the steps that are embedded when you do rational expectations that we kind of take for granted. Actually, if you teach, you teach graduate students now, rational expectations is so widely accepted, its foundations are forgotten. Not that anyone should care about that, but I found it interesting. Because when rational expectations started, the old guys, like me, They hated it. They said it was completely foolish. This communism thing was incredible, you know. But now it's completely bought. Okay. So now here's the question: does uncertainty aversion resemble risk aversion? The answer is yes and no. In some ways it does, in terms of its effects on asset prices, but in other ways it doesn't. So there's these classic questions of Krebs and Porteous and Duffy and Epstein, of asking how people care about the intertemporal resolution of uncertainty. And these min-max preferences separate risk aversion from attitudes about those things. So what the person that Lars and I write down is the person particularly hates the persistence of risk. He really hates that. The expected utility guy doesn't care whether risk is persistent or not. He's indifferent to it. But our guy hates it. And that's kind of key to that. Okay. So then here's the thing that concerns Lars. Here's the question. Can a small amount of uncertainty aversion, a small ball of models, substitute for a large amount of risk aversion? See, if that was true, it would be great. Because it means you could explain the equity premium and those things by saying it's by along Knightian uncertainty, or if you want Keynesian lines, that it's not risk aversion, it's something else doing it. And the answer is yes. So you have to ask what small is, how big the small is. So Lars and I have a way of thinking about these with Evan Anderson, about thinking about what's a reasonable amount of model uncertainty. So it goes like this. So you know the classic Arrow-Pratt ways of inducing your measure of curvature of your utility function. I ask you the following question. Okay, good. I ask you the following question. How much would you be willing to pay to avoid this well-understood risk? You tell me, I can compute your risk aversion. And it would be, your gamma would be 1 or 2. To explain the equity premium, it has to be 10,000. Okay, so now what I do is our experiment is, here's an approximating model. Here's a ball of models. Take a model on the boundary, 2 models, and I ask, how much data would you need to distinguish those 2 things with confidence? It's a very different experiment. It's a very different experiment. So Lars and I use this with lots of things. So so this opens up a lot of things. So I don't know if you know, there's a famous paper. I think it was badly timed. It's Lucas's presidential address to the AA, and it's like, what are the costs of business cycles? And basically he takes the exogenous it's fine to take it as the post-war per capita consumption process in the United States. Okay, and he says, that's what Greenspan and Volcker gave us after all their good job. Take that thing, plug it into summation beta to the t, u of ct, take the expected value. And then ask, how much would you have been willing to pay to eliminate the business cycle? Do you see that? Turns out to be a small number, and the number turns on what I assume is about the curvature. He takes an estimate of the curvature, which is 1 or 2 by introspection, even though it takes 1,000 to explain the asset prices. And interesting discussion in his thing is why he doesn't care about asset pricing. And it's actually beautiful because he says, I reject the Lucas asset pricing model. That's what he says. And then he has a line in there. He says, it would be great to explain the equity premium puzzle, but it can't be risk aversion that's doing it. And risk aversion, I shouldn't pull my risk aversion parameter from the equity premium. So then what Lars and I do is we say, well, there's another experiment, and it is this. How much, okay, so we start evaluating consumption streams not just under this process that Lucas estimated, but under these alternative processes that are nearby. Anyway, you get in there. That's enough. Okay, I'm going to quit. Okay, so now, how does it affect government policy design? And I'll just conclude with this. Now here you're going to wish you were a communist for the following reason. Now I've put multiple agents on the table. So the question is, who fears model misspecification? And who has the high ground? So I'm going to put in a common approximating model, as that's done all over Ramsey taxation or Mealy's taxation. The Harsanyi doctrine or communism rules that literature. But now we're going to start a common approximating model, fine, but we're going to add some doubts. Who has the doubts? And what does each player understand about the other person's doubts? I'm going to have to go down this road.